Okay, today our goal is to learn how to locate an earthquake's epicenter, which is basically one of the most important things that scientists want to know. So let's say there was an earthquake that shook Chicago, and people in Chicago felt it, and people here in Glen Ellen felt it, and then people in southern Illinois felt it. Well, there's all these different places that feel the earthquake, but how do we know where it actually started and how strong it actually was? Because each of those places, based on how close they are going to feel different things. So today we're going to explore that a little bit. Last week we talked a lot about earthquakes, right? We talked about basically how an earthquake's very center start, especially on land of when we feel things, is called the epicenter. And we also talked about that there's different waves called seismic waves that are generated in an earthquake, right? And we talked about how the first kind of wave that is the fastest but does the least amount of damage is called a primary or a P wave. Then we talked about how secondary waves come next. And then the last is most destructive, and that's the crazy surface wave, right? Well, scientists actually use machines and record those waves as they are felt with the ground shaking and use that recording to figure out where the epicenter was and how strong the earthquake was. So if we look at this, you saw this last week. This is a seismograph. Seismograph is a piece of technology that's all over the country. There are hundreds of them in a whole bunch of different places. Some of them are kind of even random. Like there's some fire stations that have these. But basically, seismographs vary in size, and they look like this. It's basically an instrument that has a weight that's attached to a pen and a rotating drum. And basically, when the earth moves, the weight moves back and forth. And so if the earth moves a little bit, the recording is going to be kind of a small little wave. But if the earth moves a lot, it's going to be a much stronger, faster, higher wave, right? So if we look at this seismograph that's in the wall here, it's a little more sophisticated. We can notice all the way on the left side that there's tiny little waves generated, right? That was kind of a smaller earthquake. But then this one that's over on the right-hand side, much larger waves, right? That obviously caused much larger shaking in the earth. So basically, these seismograph stations, so this is a seismograph, and they can also look like this, are all over the world, right? And when shaking happens anywhere, these seismographs are ready to go right away and record it. When they record information, it ends up kind of looking like this. I almost think it looks like it's a heartbeat or like somebody's having a heart attack or, some kind of echocardiogram that monitors your heart. But this is basically what is generated by these seismograph machines. As they generate these little print-offs that look like little waves or like little murmurs of the heart, right? And basically, if they want to know where an earthquake occurred and how big it was, they have to use information from three different places. So again, here's what a seismograph looks like. Let's say Chicago, or a seismogram. Let's say Chicago felt the earthquake and here was its print off. Let's say we felt an earthquake and we printed a seismogram, and then Southern Illinois printed a seismogram. You've had three of these. Based on looking at data from three of these seismograms, you could pinpoint exactly how big the real earthquake was, and also how far away it was, the epicenter. So basically, by looking at each of those stations individually, you can pinpoint where it actually happened. So let's say there was shaking in Portland, there was shaking in Salt Lake City, and there was shaking in Los Angeles. Well, they all felt shaking. So how do we determine where it actually started and how strong it was? Well, the process we're going to go through today actually triangulates or pinpoints a location of each of these to determine where the epicenter is. So we're going to go through a little simulation that does that. So what you want to do is go to your screen or to Google Classroom, and you want to click on You're a Seismologist. When you get there, you're going to see Mr. Seismologist right here looking at a seismogram, analyzing data, and you want to click on the link. Okay, it's going to take you to a screen that looks like this. All right, let's go back. So basically, we're going to fill out this information that we just did together. So number one, scientists always want to know where the blank of an earthquake is located. Well, that should be epicenter. Okay, and then in general, data from three seismic stations, right? We want three seismographs are going to be needed to determine the epicenter. So we can't just look at one location and say, oh, that's where it happened, because the shaking is felt in multiple places, right? And then the instrument that generates a report is called a seismograph. A seismograph. So make sure you copy those down. Okay, so now what we're going to do is we're going to simulate an earthquake in the United States, and we're going to pretend that it's felt all over the place. But we're going to use data from 3 seismograph machines to figure out where the earthquake actually originated. So the first one we're going to do happens in the United States. So we're going to go back to that website, and we're going to click on the United States, and you'll notice some shaking. Ooh, there we go. Okay, and basically what it says is that they felt shaking in Los Angeles, Las Vegas, and this place called Roseburg. So if you look at the map on the left, you notice all those places, right? If you notice, it looks like the highest waves, the strongest, the most violent waves happened in Los Angeles, right? So our earthquake probably started closer to Los Angeles. And then if you look down at Roseburg, very, very, very tiny waves. So the earthquake was probably the farthest away, right? But we want to get that exact. So we're going to have to look at these seismograms. So we're going to click on next. And then we're going to look at each seismogram. And basically, one thing that you have to notice with the seismogram is you have to look at the difference in time between the very first wave and the second wave. So what is the time difference between the first P wave or primary wave and the secondary S wave? So all you have to do on this is take a look at when the actual waves start for the first time and the second time, and look at the time interval in between. So if we look at this, we notice that it's a little under 50. So I'm going to put 46. It's pretty dummy proof. If you get the wrong answer, it'll tell you that you didn't get the right answer. But 46 seconds between the first and the second wave in Los Angeles. So I'm going to go ahead on my sheet. I'm going to put Los Angeles. And what did we say? 46? Oops. Said 46. Good. 46 seconds. 46. Okay. So Los Angeles, between the first and the second wave, there was a 46-second delay. Let's look at our second location. The second location is Las Vegas. Look at this one. P wave started obviously at 0. The next count is around 60, probably 61. So let's look at 61. There we go. So I'm going to put 61, and that's Las Vegas. So I'm going to now type in Las Vegas. I'm going to put 61 seconds. So it took a little longer at that time, right? Which probably means it's further away. That makes sense. And then the third location, let's click on Roseburg, was so tiny, but look at how long between the first and the second wave. Like 71 seconds, it looks like, right? 71. So now I'm going to type in Roseburg, 71 seconds. Okay? So now I have the 3 cities and how far apart the waves were. So the next part that we're going to do, it's a little confusing, but we're going to use a graph. And basically what scientists do is they plot the seconds that it took between the first and second wave, and then they follow this line that goes down the center, and that tells them how far away the epicenter was. So in Los Angeles, it took like what we say 46 seconds between. So if we go all the way down here, according to Los Angeles, somewhere around Los Angeles, that epicenter was about 450 kilometers away. So I'm going to write, it's about 450 kilometers away. Okay, so somewhere around the area of Los Angeles, if you go any direction, 450 kilometers, that's somewhere around that circle is where the earthquake happened. Then you're going to do the same for Las Vegas. Las Vegas, if they had about 61 seconds, it looks like about 600. So Las Vegas is 600. I'm going to do one more. Rosenberg looks like it's about 7. So 6 and 700. So I'm going to put 600 and 700, which makes sense because the farther away it is, I'm going to feel it less, right? So let's answer the questions. Which city would you expect to be the most impacted? Well, looking at the data, we'd probably go back and look at which one had the most, in terms of how far away it was and how the seconds were, right? So if we remember on our seismograph, the most severe was Los Angeles. So we'd say, where would the most impact be? Los Angeles. Okay. And then which city would be the least? Probably Roseburg, right? And again, we know that by the distance, and we also know that how strong it was, right? And how long it took. Okay, so now the last thing scientists need to figure out, oops, I'm sorry, I'm jumping ahead of myself. So now let's, don't worry about these questions, just keep going with that. But I'm just gonna fill that question out. You don't have to fill it out on your sheet. So here's the coolest part. So scientists, like I said, are gonna take here's Los Angeles, right? And we know that the the epicenter is somewhere around 450 kilometers away. So they make a circle 450 kilometers around Los Angeles, and it must have happened somewhere on this red line. Then they do the same for Las Vegas and make a green line. They do the same thing for Rosenberg. So those are where all those machines predict that the earthquake epicenter is. But what's kind of cool is basically they triangulate the data wherever all three circles meet. So where the purple, the green, and the red meet, boop, is where the epicenter actually occurred. So if you notice it, it's really closest to Los Angeles, right? So right off the coast of California is where the actual earthquake started. So even though all these places felt it, here's where it actually started, which is always what scientists want to know to report. So there's the epicenter. Okay, so I'm going to click next. The next thing I want to know is how big the earthquake was. How much do they feel? Because in each location, based on how close to the center it was, right, they're going to have different amount of shaking. So we're going to look at the magnitude. So let's look at Los Angeles. Remember, Los Angeles had a really big wave. Now we're going to look at how tall the wave got. So it's what's called amplitude, how much power there was or strength. And if we look at this, the tallest wave was about, like let's say 280, okay? So it's 280 millimeters. So we're gonna put 280 under here, whoops, okay? Then let's do my next two locations. Then I'm gonna click on Las Vegas. And if I notice, here's the P wave, here's the S wave we did before, but I actually wanna look at this now. So I wanna look at how tall the wave was. Well, the wave is just a little bit under 100, so we'll say 90. Okay, so I'm gonna go back and put 90 down here, okay? And then the last location, Roseburg, is, oh my gosh, tiny little wave, right? Just under 50 or right about 50. So I'm gonna click on 50. So I'm gonna go back and put 50. Okay, so now we know how strong it was, right? Which makes sense. 280 is a much bigger wave in Los Angeles because they were clearly closer, right? Okay, so that makes sense. So here's what scientists do now. They put this on a thing called a nomogram, and basically they just connect and draw lines between the two. So they draw a line by clicking on the red dot, on the green dot, and the purple dot. Wherever those three intersect is how strong the actual earthquake was. So even though these places felt strong or not as strong earthquakes, the actual earthquake, if we click next, the actual amplitude, how strong it really was a 7, which is a big deal. A 7 can cause a lot of damage. So let's go to what was the magnitude of the earthquake. That's a 7. Okay, and basically, the next question has you answering what would happen. And basically, Los Angeles, there would be significant damage to buildings and highways. Okay, so what we're going to put, because this on the Richter scale, which measures how strong an earthquake is, 4, like on a scale from 0 to 10, 4 you would feel it. So 7, you're starting to notice some significant damage. So we're going to put 7 there. The impact would be like lots of damage and destruction to buildings. Okay, and then the last one, we would just click next, and then it tells you where it was. It was in this area called Loma Prieta, but we know it was close to Los Angeles, right? So we'll say outside of Los Angeles is where the epicenter was, right? But this way now, scientists and people on the news can then say, hey, outside of Los Angeles today, there was a magnitude 7 earthquake that affected people around the area, right? And so they would know the location of the epicenter and how strong it was. So that's how you do that simulation. I know that took a while. So here's what I want you to do. I want you to either pick and go back to this website, either pick now Argentina and make an earthquake there, or pick Japan and see if you can do the same thing we just did. Do this process over again like seismologists do and see if you could figure out where the epicenter is. So on your sheet, you're either going to fill out map 2 Argentina, just like we did with map 1, or you're going to fill out map 3 Japan. And whoops, I left my answers here. Whoops. But that's what you're going to fill out. Once you have the first example that we did together and a second one, just do 2 of them, turn it in, you're done for your work today. Okay? Have a great day.